This is the first distinguished lectures for the Allen Institute for Artificial Intelligence. So I'll just say a few quick words of introduction. First of all, about the Institute. It's Paul Allen's brainchild, and I'm directing it, and pretty much the entire team of talented people is here, which is great. And we welcome our guests. We hope to bring to Seattle terrific thinkers and speakers in questions related to AI, and I couldn't think of anybody better to launch this series than Gary Marcus, who's a celebrated author. He's got a popular New York Times bestseller. He's got 4 books, including Kluge, which I read. Is a terrific book about the mind, and he's also really one of the leading thinkers of our time about cognitive science, AI, the various issues, and he blogs about that for the New Yorker in a blog that's widely read by people in the community. And today he will tell us about smart machines, etc.
Thanks very much. Very kind introduction. I'm very glad to be here. You will see it's a weird room where the screens are opposite ends, so I don't know how we're going to manage the eye contact part of this, but if you look at bottom, you'll see that I'm now a regular visitor. So I'm not just giving a talk today, but I'm coming back. I'll be back every 2 months or something like that. So I hope to get to know many of you over those return visits. I don't have my email up there, but I should have. It's gary.marcus@nyu.edu. So if you know my main affiliation and my name, it's very mnemonic. And I am proud to say that I was just given a badge, so I feel like I'm an honorary part of the team. I'm happy to be
badge carrying member.
That's right. I'm now a badge carrying, first time in my life. I want to start by thanking Ernie Davis, who I've been collaborating on AI projects with for the last year or two. As I have come back from cognitive science to AI. I first started thinking about AI when I was a little kid trying to program my Commodore 64 in Logo. I got into college on the strength of a Latin to English translator that did maybe a semester of Latin using the language Logo. So I used to be very interested in AI, and then I took a long detour into cognitive science, experimental work on children learning language and so forth. And then in the last couple of years, I've gotten very interested again in AI, and a lot of it has been in collaboration with Ernie Davis, who works on things like common sense reasoning. We have a critique of the Bayesian movement in cognitive science that I'll allude to briefly. I think we've been doing lots of really fun things together, and probably, though not every word of this is his, I've discussed probably all of it with him, so he certainly deserves special thanks. So the other thing I should say is I'm a little bit preaching to the choir probably in giving this talk. I think that a lot of the people that might think differently are not in this room, but elsewhere. You'll see what I mean. But I'll warn you in advance that I think you'll probably be closer to my side than, say, people who do a lot of deep learning, which I'm guessing is not the focus of at least most people in the room, but we'll see. Okay, so as you all know, there's been a long-standing dream of artificial intelligence. There's this famous quote from Herb Simon that's possibly in too small a font there, saying, you know, basically that AI is on your doorstep. And then I have a quote from Marvin Minsky in 1961 and Rick Kurzweil in 2008. Everybody's saying AI is you know, around the corner. But there's actually this interesting study, I don't know if you guys all know it, where somebody actually tabulated all the guesses that were in the literature for when AI would come. And there's 2 things to say about it. First is, it's sort of a normal distribution, centered around 16 to 20 years. So if you ask people, when is AI, I mean, strong AI, going to arrive? The answer is almost always 20 years. And the interesting thing about that is, if you look at this graph, the answer doesn't matter when you ask the question. So people said 20 years if you asked them in 1957, and they say 20 years now. It's always just far enough that you can apply for a grant for it. Okay. Of course, there have been some significant victories. I don't want to say that nothing has happened since 1957. Obviously, a lot has. So it's pretty impressive that machines have beat humans in chess, and it's, I think, even more impressive that they beat humans in Jeopardy, although there's a secret trick to that I will reveal later. But there are also lots of problems that remain unsolved. So I would say that machine reading is still not at a 4th grade level. If I were more careful, I'd probably say machines can read a few things at, you know, a college level, but most things they can't. can't even read at the 4th grade level. Common sense reasoning is still spotty at best. Natural language understanding is really limited to specific narrow domains. There's this great advertisement from Apple about what Siri can do. It says you can ask about movies, you can ask about restaurants. And the thing is, that's all you can ask about it, but they make it sound like it's a list and you generalize the notion they might actually understand you, which is not true. Scene and sketch understanding are still pretty limited. You can't, feed in a cartoon and expect the machine to tell you what the cartoon is about. It might be able to tell you what the characters are in it. There's been progress. It's not going to tell you what's going on. The ability to acquire new complex tasks is still pretty limited. I mean, you can download an app for a particular thing, but you can't just tell a machine, well, this is how this game works, and I want you to go play it. People are starting to work on it a little bit, but I think it's fair to say there hasn't been much progress there, or more generally, in what some people would call AGI, artificial general intelligence. There are lots of core problems, probably you could come up with more, that remain unsolved. Unfortunately, and this is where my background in cognitive science comes in, we still don't know how natural intelligence works. Now, it's not an absolute logical prerequisite that to build smart machines, we'd actually know anything about how human minds work or other smart, intelligent animals, but certainly we would like to get as many clues as we can, and I think that that's what I can bring to bear. So we still don't know how natural intelligence works. It's not that anybody hasn't tried. So this next part of my talk is kind of going to be a critique of the efforts people have taken to try to understand how the human mind works. There have been lots of theories. For example, behaviorism was a nicely worked out mathematical theory that made all kinds of very precise predictions about what learning regimes you might have and what you would know as a consequence of what you would do next. It was very popular. It completely dominated American psychology departments during the 20s, 30s, and 40s. People like Skinner were basically household names with bestsellers and so forth. But it couldn't account for language. Probably there are other things I could suggest it couldn't account for either, but his basic sort of stimulus response history kind of theory turned out not to be very effective, and Chomsky basically crushed it in the late 1950s. Now you can't find, except in the departments where there are a few people that probably should retire, you can't really find any sign of behaviorism. It basically vanished even though it was completely dominant for a long time, which is embarrassing for my native field of psychology. There have been other embarrassments as well. So parallel distributed processing became extremely popular when I in college started studying cognitive science. You couldn't really go anywhere without seeing these two books, blue and I guess the other one was sort of shaded brown. I'm not so good on color. That people called the PDP Bibles, the Parallel Distributed Processing Bibles. Some of you were young enough that you weren't alive then, so you may not be familiar, but there was a period when this was completely dominant in cognitive science. There was a line from Paul Smolensky, who was one of the leading figures in the field, saying that the conferences of cognitive science started to seem like connectionist, which is another word for these kinds of systems, connectionist cheering sections or something like that. So it was totally dominant. It was dubbed a paradigm shift. People would write articles about how we had completely gotten rid of classical cognitive science, classical psychology. We had this new way of basically understanding the brain as a set of abstract nodes with the connections between them that you would tune over time. I'm going to show you some examples in a moment. They were always, or generally initially random. You'd have a supervisor, you'd have input-output pairs. Totally dominant, and again, language turned out to be the place where these systems failed. And by the early 2000s, I think they had largely faded from view. Now, there's a descendant of those models, which is deep learning, that I'm going to talk about a little bit later. But I think that they're likely to have some of the same limitations. Then there are things like evolutionary psychology, so another fad perhaps in psychology. I think evolutionary psychology has something going for it that most fields of psychology don't, which is, whereas most fields in psychology give you a set of facts, evolutionary psychology actually tries to explain those facts in terms of biological history of our species. I think that's a good thing. So it's not enough to just say, well, your memory holds 7 plus or minus 2 things, which turns out to be wrong. We could talk about why. But it's not enough just to give some number. You want to say, well, why does the brain do it this way as opposed to some other way? Oren mentioned my book, Kluge. My book, Kluge, was actually an attack on evolutionary psychology, even though I was trained in some ways as an evolutionary psychologist. I think that evolutionary psychologists are right to think that the mind is a product of evolution, but they often try to explain everything in terms of superlatively well-engineered functional designs, which are bold-faced in tiny font there. So the idea is that you could figure out what the mind does by just saying, what would be the best solution? And what I tried to argue in this book, Klooge, is that there are other things that contribute to our biology too, like our evolutionary history. So the spine is not the best solution to holding up a bipedal creature. It's actually a lousy solution, but it's a compromise of a sort between the genes that were already in our genome through our primate ancestors and the niche that we started to enter, being bipedal. So I think evolutionary psychology was simplistic, but in any case, I mean, you could make a better version of it, but the popular version is simplistic. But in any case, it's starting to fade. It was completely dominant in the 1990s. You had Steve Pinker in Time magazine as the evolutionary pop star and so forth. I don't think there's been any real bite in AI that I can think of, except some people have played around with evolutionary algorithms, but I don't think they've been that successful. People might want to disagree. And I think the latter-day offshoot of evolutionary psychology, though not everybody would describe it this way, are the Bayesian accounts of human cognition that say, basically, there's this equation. If we follow this equation, we will be doing the optimal things. And there's a lot of evidence that in some domains, and here Josh Tenenbaum lists some in very, very small font, our sense of similarity, of representativeness, randomness, and so forth. There are a bunch of examples where Tenenbaum claims you can actually model what the human being is doing by supposing that there's a system of priors and you follow Bayes' rule. The problem that Ernie Davis and I just pointed out in psychological science is that for every domain where they have argued that there's some optimal process, like intuitive physics, they say, this problem, humans do this thing that seems to be optimal, seems to be basically a Newtonian physics simulator. There are apparently non-optimal counterparts to it. So another example is they have this, Griffiths and Tenenbaum have this lovely study showing that people can get some small piece of data and generalize it very nicely. Like, a given person has been in the Senate for 16 years. How many more years do you think they'll be in the Senate? And people give surprisingly reasonable guesses based on what seem to be maybe knowledge of empirical distributions of how long people spend in the Senate. And so they conclude that everyday cognition is optimal. But what Tenenbaum and Griffiths don't do is to look at other literatures where people make ridiculous extrapolations. Like, I can say, I want you to take a dollar bill out of your pocket, look at the last 3 digits, and then tell me what year you think Attila the Hun roamed through Europe. And you will be influenced by those 3 digits on the dollar bill. So there is a kind of juxtaposition between cases that seem to be optimal and those that don't. I wouldn't want to argue that we can't use Bayes' rule. I think that the brain is built such that in some domains it can at least approximate it. So in sensory motor transformations, where you get an enormous amount of data, we come very close to Bayesian optimal solutions. But I wouldn't want to argue, on the other hand, that that's a good general characterization of how human beings do things like reasoning. So I expect that that will fade in time. Another thing that is on the table as a possible AI technique, and certainly people are talking about it in neuroscience and psychology, is whole brain emulation. I think this is a great idea in the very long term, but it's pretty unrealistic in the short term. So you may know that Henry Markram has just gotten €1 billion, of funding in the EU to try to build a whole brain emulation. I'm skeptical. As you may know, we still haven't even modeled in particularly impressive detail the C. elegans roundworm, which has 302 neurons, which have been mapped out at the connectomic level for about 30 years, and we still haven't cracked that one. So the thought that in the next decade that we're going to figure out how an 86 billion neuron brain works seems to me to be implausible. At the moment, we don't even know what the basic units are to model. I gave a lecture about this at the Allen Brain Institute yesterday. We still don't really know, like, do you need to account for the synapses? Do you need to account for individual ion channels? We don't know exactly even what we're trying to model. It's pretty likely, though, this depends on the last point, that any model we might build right now would be vastly too slow to simulate a human brain in real time. And in terms of building AI, we don't actually want a faithful model. We want a scientific understanding what the brain does so that we can bring that to bear on questions about how to build better AI systems. We don't literally want to replicate human beings molecule for molecule. That's not the objective here. Peter Norvig has a funny line about, I've already made 2 human-level cognitive systems. So that's not the goal of AI research. Though as a new father, I think it's a very cool thing to do. Okay, so whole brain emulation is probably not the right way to go either, at least in the short term. So the point is, over time, we've had a lot of theories about how the brain works, and also these have also been correspondingly brought over to AI frequently. And most of them have fizzled over time. So they each have some truth, and they have the cases that they capture pretty well. But there's a depressingly common arc, which is initial success, great enthusiasm, declaration of paradigm shift, and then people kind of run out of low-hanging fruit. They don't know what to do next, and they go on to the next thing. So why do we have so many of these cycles of boom and bust? I think there are 4 primary causes. The first, I think, is a lust for silver bullets. Too many researchers, not I think in this room, this is where I think I start to be preaching to the choir perhaps, but too many researchers are looking for single uniform learning architectures to solve all problems. I think the most recent version of this, maybe he'll be offended, but I think it's probably fair, is Andrew Ng has been arguing that deep learning can sort of knows no boundaries. We were at a conference together recently, and he pretty much stuck to that line. I would bring up things, and I was asking questions at his talk, and he would say, well, we don't know for sure yet, but his notion was, you know, we'll get there with deep learning. And I think that the reason that people like silver bullets is simplicity sells, or maybe it's a restatement of the problem. But in all of these popular theories, and a couple others that I didn't mention, one other I didn't mention, there's a very simple ontology that you can explain to people in 10 minutes or an hour or what have you. So in behaviorism, you had a very simple ontology of things that you represented in your model of how the mind works. You had the response reward history, and that was it. You could derive everything else from there. In parallel distributed processing, you had input nodes, output nodes, connections, hidden units, and a backpropagation algorithm. That's all you really needed to know. In about 20 minutes, I could get you the algorithm, and you were good to go. Bayesian approaches, it's kind of the same thing. Evolutionary psychology is kind of a one-liner, that the mind is adapted to the problems that our ancestors solved. And Chomsky, in his own way, is trying to have a kind of one-liner explanation of linguistics, where everything is derived from, as he puts it, virtual conceptual necessity. People find these ideas attractive, but that doesn't make them right. In fact, there's no reason whatsoever to think that the brain itself is actually simple. At the top left, I have a picture from Van Essen and Velleman, in other order, in 1991. It used to be you could not go to a neuroscience talk without seeing that figure, which is supposed to be part of 32 areas that are in the visual system, showing their interconnectivity. And the first thing you notice, especially at this small font, is it's very complicated. It almost seems random, but it's actually systematic. So there's enormous complexity. I didn't have time to add this new figure. There's a paper that was in Science last year where they've actually looked at more cortical areas. It turns out that it's not the case that only some things are interconnected with others, but actually everything is pretty much interconnected with everything, but they vary in 6 orders of magnitude in terms of how dense those interconnections are. So there's enormous complexity in the brain in terms of kind of area-wise connectivity. So how does the visual area, V1, connect to the other areas? There's also, as in the top right figure, enormous complexity if you look at the basic stereotype of the 6-layer cortical sheet, which is at least roughly uniform across the brain, though my talk yesterday was about some differences. But even if you just take the basics of the 6-layer cortical organization, it's pretty complicated. When I look at the kinds of models people have proposed in AI when there's a single learning algorithm, I don't see any match between that and the complexity we see here. At the bottom left, I have a figure that's not even beginning to capture the complexity of different individual cell types. I got a wonderful statistic the other day. The mushroom body, which is part of a fruit fly, just that tiny piece of a fruit fly brain has 55 identifiably different kinds of neurons. They're estimated to be on the order of maybe several hundred in the human brain, but nobody knows for sure. And then the bottom right is showing some of the complexity in the molecules involved in individual synapses, which apparently can differ from each other in identifiable ways. We don't know what that complexity is for, but I think that the take-home message here is pretty clear, which is whatever the brain's doing, it's pretty complicated. We shouldn't expect a silver bullet, one simple algorithm that's going to actually capture that. I think the second cause of kind of the boom and bust cycles and in general some of the limitations of the field is an excessive love of empiricism. So as a kind of example, I have a paper from Science about a little over a decade ago where they talked about autonomous mental development by robots and animals. And basically the way that these researchers went about the problem was to start with robots that knew nothing, put them in some kind of experiential situation, and hope that they would learn about the world. And I think basically 12 years later, these robots are stuck at the one word stage. So you can, the robots are much cuter, as you can see from the picture. But if you watch videos of what they're doing, it's basically look at the ball, and a graduate student holds the ball and goes back and forth as if it were a 12-month-old child, same age as my son. But my son, I think, is already generalizing more than the best robots out there. And I expect that he will exponentially take off, whereas I'm not so sure about the development of robotics. Third cause, I think, is a kind of neurophilia and also physics envy. So people like math, they want things to look brain-like. And so if your theory has a kind of brain-like flavor to it, as parallel distributed processing does, then people get very excited about it, even though it probably isn't really capturing much of the actual detail. So I have, this is probably the most, what's the word that I'm looking for? The most objectionable slide in my talk. I have a list of AI systems that owe their design on the left, largely discoveries about how the human brain works. And I list optical character recognition, check reading, license plate recognition, Google's cat detector, which I'll talk about in a minute. And then I have on the right AI products that owe relatively little to neuroscience per se, and I wrote down nearly everything else. I'm sure some people will want to object, but I tend to think it's true. Certainly that would include Watson and Deep Blue, which have a little Susan, I think is the word, of neural network stuff. Watson does, but it's hardly the driving force behind Watson. So most of what you see in actual effective systems, I think, is good old-fashioned artificial intelligence, even though people don't want to talk about it anymore. A lot of Bayes, which was not in the classical artificial intelligence literature, and then hidden Markov models of some sort or another, and then a tiny bit of neural nets that aren't particularly biologically realistic. So I don't think we have any concrete evidence that building brain-like computational models is the right way to go. Arguably the best in breed might be Hawkin's Numenta, which promises real-time predictive analytics, which sounds great if you could have it. You stick in your problem and out comes an answer. You don't have to wait around. You don't have to know anything about it. You just crank it like a cranberry grinder or something like that. Out comes your results. And it actually is a decent model of at least some aspects of the brain. I think that as far as these things go, I think Hawkins has thought pretty deeply about how the brain works. I think he's thought in a kind of narrow way, but the part that he captures, I think, is reasonable. But after a decade, there's still very few concrete results. I just discovered that if you'd like, you can actually grab some version of the code on GitHub and you can play around with it yourself. But I haven't seen any convincing demo that it can do anything better than anybody else can. The fourth cause is what some people call the fallacy of hasty generalization. There's a joke that's a version of the example that Wikipedia gives. The example of hasty generalization that Wikipedia gives is a person is looking at a number line, 3 is a prime number, 5 is a prime number, 7 is a prime number, 9 is probably an anomaly, so it's ignored, 11 and 13 are prime, and therefore the person says all odd numbers are prime. I won't do the whole joke. I actually just retold it in The Guardian if you want to look it up online. It's not my joke. The joke ends with the artist going, 1 is prime, 3 is prime, 5 is prime, 7 is prime, 9 is prime, 11 is prime, and so forth. Psychologists just think it's statistically significant. In any case, hasty generalization is this notion that you have some small set of examples and you go too far with it. Well, I think that that's really what haunted, ultimately, parallel distributed processing. People found models that seemed to be good on the low-hanging fruit, and they just said, well, if we can get the low-hanging fruit, we'll go all the way. And I think Zen Empiricism maybe was the person that said this is like saying that if you can build a ladder, you can get to the moon. This is a very common error, I think, in AI research. I think probabilistic models of cognition are headed for the same kind of collapse. That's what the Marcus and Davis 2013 Psych Science paper is about, saying, look, there are these cases where they work, but there are these other cases that are right next door that are being ignored that don't work, and this is a bad sign. I suspect that deep learning is going to fall out similarly. I think there are real industrial applications for it, but I don't think that it's anywhere near the panacea that someone like Andrew Ng seems to think. What I want to do now is to give you a case study of hierarchical feature detectors, and I choose them for a number of different reasons. One reason is I think that the most dominant paradigm in computational neuroscience, almost, well, I don't know what the, I'll say the majority of computational neuroscience models are variations on hierarchical feature detectors. It's also the case that deep learning, which is kind of the flavor of the month in AI, is a variation on hierarchical feature detection. I think There's real reason that you might want to build systems to do this. I think there's real reasons to think that this is part of what the brain does. And I also think there's real reasons to think that the scope of these kinds of systems is ultimately limited. So what I mean by a hierarchical feature detector is you recognize the letter A by first recognizing things like there are vertical lines or diagonal lines, and then you have successively more abstract features like there might be two pieces and a vertex that connect and so forth. You get more and more abstract as you go up the hierarchy. I associate it with Hubel and Wiesel, who gave some pretty good evidence in cat cortex and maybe monkey cortex, showing that things like this actually exist, that you have cells that are what they call simple cells, then more complex cells, hypercomplex cells. I think these things are real. I think it's as good as far as it goes, but it doesn't go far enough. They're pervasive in AI. The neocognitron model is one that even the younger people in the room should know about. I'm sure the older people do. It's basically an instantiation of this kind of idea. Hawkin's model is a version of this idea, and deep learning is a version of this idea. What's cool about deep learning is it does a much better job of learning the features. So before deep learning came along, lots of people played around with these models, mostly in vision, to some extent in speech recognition and so forth. And you would take a human engineer, look at the problem and say, what is a good way of building these abstract features so that at each level the features are recognizable as a function of the parts that precede them. So there's a lot of human engineering that went into that problem. And it turns out that you can get the deep learning algorithms to do a pretty good job of automatically identifying the features you need. Sometimes those are features that human beings might not themselves have thought about. So I think there's been a real advance there, despite the critical things that I will say. So I think that there is a real advance there, but I do think there's a limit to that too. Probably the kind of ultimate version so far of this, at least that's been publicly disclosed, is Google's cat detector. I imagine most of you know about this. It was on the front page of the New York Times. This was a massive, massive hierarchical feature detector that was trained on stills from millions of YouTube videos, and you could do something equivalent to neuroscience techniques on it. You could go through and you could look at its so-called neurons and ask, what are the receptive fields? What do these neurons respond to? What is a template for this neuron or that neuron? And they discovered that one of them responded to cats. Turns out, by the way, not coincidentally, there are a lot of YouTube videos of people's cats, and so they were disproportionately represented in the sample. So the cat detector is in some ways impressive, but it's still not there yet. Its accuracy is about 15.8%. Don't actually have human data for the same sample, so I'm not quite sure about comparing humans on that, but I am sure about the other part. They do give data, which nobody seems to have noticed, on scale invariance. So what if you make the cat bigger or smaller? Rotation, what if you turn the cat around? Translational, so you move it left and right, and so forth. And it's nowhere near on human performance. If there's a cat bang in the middle of the frame, then it does, of the right size, then it does a good job and it starts to fall away. I'll come back to that, a system like that a little bit later. Deep learning is even weaker when it comes to natural language understanding. As far as I know, the state-of-the-art system is one by Richard Socher. I don't quite know how he pronounces his last name, graduate student at Stanford working with Andrew and maybe some folks at Google. And they have a sentiment analyzer, which you can all play around with. Forgetting the title of it. If you look at my last New Yorker piece, there's a link to it. Deeply Something is the title of this thing. And the idea is you feed it in a movie review. And so I typed in better than cats, and it told me that's a very positive review, which was correct. And then I went to look at for a review of the next movie that I saw. I went to Rotten Tomatoes, and it said the review was a sloppy, miscast, hammed up, overlong, overloud story that still sends you out the theater on a cloud of rapture. So I think most of you can put that together and realize it's a positive review despite its nitpicks. This system, on the other hand, what it does is it makes a kind of syntactic tree. The tree itself is kind of dubious, but I don't think we need to go into details about it, but you can come up afterwards and I'll show you. But it labels things like a sloppy, overlong, loud story correctly as negative, but then at the top level it gives a negative node, says the whole thing is negative. It's completely missed the point. And this is it must be pointed out, it's not just that it gets this kind of example wrong where there's negation, for example. I'll give you one more case. But that this is actually a very narrow notion of language understanding where you would map everything onto a single dimension, like positive or negative, loved it or hated it, there's no room to ask it questions as you might ask a 6th grader, tell me something that the reviewer liked, or was the reviewer being ironic, maybe be a 7th grader or whatever. In New York City, you'd be a 6th grader. So you can't ask any questions of it. All it does is map all of its inputs onto a single dimension, and it does that poorly. Then Ernie Davis, I sent him the link, and he came up with this one. I changed one word. No one interested in the subject can afford to ignore this documentary. And outcomes, oh, that's a really negative review. All right. So why do these models keep failing at language and higher level cognition, right? This was the problem with Skinner's model. This was the problem with the parallel distributed processing models. I haven't gone through the data on the PDP models, but that was kind of what my own work was about in the 90s and early 2000s. And give you an explanation about the PDP models that I believe applies to the deep learning systems as well. The short answer, the very short answer, you could tune out on the rest if it's too much, the next 5 slides, if it's too much technical detail for you, and just remember this, all of these models are classifier models that set up what you're learning as a series of independent classifiers. I'm classifying this word independently of that word. And using these classifier models, I'll explain a little bit more what I mean by that in a minute, is like trying to capture language by forcing a square peg into a round hole. They're just the wrong tool for the job. It's not that they shouldn't have some role in language. So for example, you might use systems of hierarchical feature detectors to recognize individual words, but it would not be an appropriate use of those technologies, in my view, to try to get them to understand sentences. It's just not built for the job. So in a book called The Algebraic Mind, 2001, MIT Press, I argued that language is an algebraic system, probably some other aspects of cognition are as well, in that you have many relationships that are defined in terms of operations of variables. So you can think about how any line of computer code works or any line of assembly language works. You've got some operation that is specified with respect to some variable. And the thing that makes the programming language work or the assembly language work is that you know in advance that that instruction will work for any possible instantiation of the variable. So for example, you might have the operation addition. You don't need to train the microprocessor on a whole bunch of examples of addition. You know as a programmer in advance that it will work for all possible instantiations of all numbers within some defined range for addition. This is, I think, the most vital thing that makes computer programming even possible, but it turns out that parallel distributed processing networks, and I think deep learning networks, don't really do this. So they're good at classification, but they're poor at capturing what I would call universally quantified one-to-one mappings. And a universally quantified one-to-one mapping is something where I can have any input, it's got its own unique output, and I can extend this to all the examples in some domain. I'm going to give you a simple example in a minute. One simple example is in the middle, you look at that function. So 0, 1, 1, 0 goes to 0, 1, 1, 0. 1, 1, 0, 0 goes to 1, 1, 0, 0. That should be enough for most of you to have a good guess what function I might be instantiating there, which would, I feel like I'm prejudicing the audience. I won't embarrass me or you by calling out, but it looks to me anyway like the identity function, right? So if I give you the input of 4 1s, what do I expect back? I expect 4 1s. Is that mathematically a necessity? Well, of course not. Induction says that there's any number of possible continuations for any pattern. But the one that humans gravitate here towards is the sequence of 1s. I actually have data that even 7-month-old babies basically gravitate to the same thing. So I had an article in Science where we gave 7-month-old sentences like la ta ta, ga na na, and basically they were an ABB grammar. So they have identity represented over time. And the kids had no trouble with this. If you changed to a new vocabulary, the point was so you couldn't use simple systems like bigram systems, then the kids would recognize that wo-fei wo was a different grammar from what they had heard before. Wo-fei-fei was the same grammar as they heard before. Then, as is traditional in developmental psychology, it's sort of like I can do anything, you can do better. In developmental psychology, the game is I can get a younger kid to do anything that you've already. So there's a recent paper where people took new methods and showed that newborns could do the same thing. They left that in control, but I think they're basically right. And then I took what was the most popular model, most popular paper in psycholinguistics for a long time was Jeff Ellman's simple recurrent network, which is a PDP model with a set of nodes that fed back in called context nodes, and I gave it identity over time. A rose is a rose, a tulip is a tulip, and asked it a lily is a blank, and it was basically the equivalent of speechless. So these PDP models could not get these basic functions that even human infants can get very easily. It's not that you can't represent a function like this in a PDP model. In fact, there's something called an auto-associator, which is like day one in your PDP network class, or in your machine learning class, I guess. So you, in principle, what you do is you train one of these networks, and I'm sorry, it's not going to show up super well, but you train a network. Let's say you've represented, your inputs are binary numbers, so you represent 12 by activating the 2 nodes that are in the lower left there, and then the output is supposed to be the 2 nodes in the top left. So you train it up on 12. You say 110 is my input, 110 0 is my output, and then you use some kind of error correction algorithm that looks at the difference between what output was actually generated and what your target output is, and adjust the weights in order to do that. Very standard approach in parallel distributed processing. Goes back to the notion of a perceptron, very old notion of perceptron. Then you give it another example. You say, now I'm going to give it 14, and over time, you start to have the correct weights in order to do that. So 14 is 8, 4, and 2 on the bottom, and 8, 4, and 2 on the top. You initially structure all of these nodes to be random, all the connections to be random. Over time, the connections that are not helping you get weaker, the ones that are get stronger, and eventually, when I feed in the same input, the model gives the right output. But if I train this kind of model on all the even numbers, and now I test it on the odd numbers, it will systematically give us the wrong answer, no matter what your random weights are at the beginning. It will systematically tell us that the one output node should remain as a 0, period. So you give it 15 as the input, and it tells you 14 as the output. You give it 3 as the input, and it tells you 2 as the output. So there's a systematic problem with these kinds of networks. One way to think about it is that each of the output nodes is an independent classifier. So the 8 node sits there, and I'm going to anthropomorphize it to make it easier to talk about. The 8 node sits there and says, well, what are the circumstances when I should trigger? And it notices some examples over time, and it says, I get it. Whenever the 8 node input node is active, I will trigger, and otherwise none of this other stuff is relevant to me. That's what it is to tune that connection. The 4 node, meanwhile, is doing a kind of parallel thing, and it says, well, when should I trigger? Well, when the 4 input node is active. The 1 node, meanwhile, what has the 1 node done? This is where you can see if you're following the logic. If you're following the logic, you should know that the 1 node is sitting there and it says, I never turn on. Game over. There's nothing else for me to do. So the 1 node, because it's being tuned independently from the others, and because it's always being told not to turn on, concludes it should not turn on. It's mathematically reasonable, but it just doesn't capture the way that humans think about these kinds of problems. And that's because humans think about them as operations over variables. They're looking for lawful things that they can do for whole classes of items, rather than parceling the problem into little bits. There might be some domains where people actually do something like this, like sensory motor coordinate transformations would be a possible case. But when we do language, we just don't do it this way. Hidden units don't help. That was what all the fuss was about in the mid-'80s. Minsky and Papert had shown that if you didn't have a hidden unit, you couldn't even do exclusive OR, so people gave up. Most people gave up on the systems. Even Minsky and Papert realized if you had hidden units, you could do something better, but they thought there was no systematic way to train the networks. And in mid-'80s, people found systematic, not perfect, but systematic ways to train networks that had hidden units, and that's why there was so much excitement, because people knew if you had a hidden unit, you could suddenly do nonlinearly separable functions, which is a whole lot broader class than just being able to do linearly separable functions. So people got very excited. That's why PDP became popular, but they don't help at all for the problem that I just described. Your output independence remains an issue no matter how many hidden units and how many layers you have. Deep learning is partly about having multiple layers. Now we have a way of training multiple layers, but it still has, I believe, I haven't tested it, but I'm pretty sure it has the same problem. The way I think about this is in PDP models, there's a training space. It's not that they can't generalize at all, and this is why they got so popular even though they were really very limited. Is because people knew that the issue was generalization, but they didn't think about it in precise enough terms. They knew it was generalization, and they saw that PDP models could generalize. So if I train the network on 8 and 4 and 2 independently, the model would be able to put 14 together, even though it hadn't seen it before. So people said, wow, these models can generalize. You thought you needed rules to generalize, but we can get generalization out of these models. What they didn't realize is there's a difference between what you might call interpolation and extrapolation. So if I give you 8, 4, and 2, and now I give you 14, 14 is within a space of examples that you've seen before, and you can handle that. There's some limits. You're not always able to do that, but you can often do that. And so as I give you more examples, you have a broader training space, you can generalize more. But in my identity example, and there are others we can construct, there's always going to be something outside the space. So if I only give you even numbers, there's going to be an odd number that's outside the space. The models aren't going to be able to generalize to it. Or I can make a bigger number than you've ever seen before. By definition, by the usual proofs of infinity, essentially. And these models aren't going to be able to generalize to that either. Okay. So hierarchies of feature detectors do an impressive job on speech recognition and optical character recognition, where what you want to do is basically identify this belongs to this class, this belongs to another class. This is an example of this phoneme or this letter or this number. If you have a finite bounded set of classes and a broad enough training space, you're done. You don't need to turn to variables. For those kinds of problems, it's a reasonable approach. I mean, I can give you some other criticism, but to first order approximation, those are a reasonable approach for those kinds of problems. But they're weak at inference when you need to go beyond the space of training examples. I'll skip the rest of the slide for now. In hindsight, the PDP craze instantiated each of the errors that I described. The models were too simple, they lacked innate structure, so they had to relearn everything from scratch. They were accepted relatively uncritical because they were mathematical, and relatively brain-like, so they kind of struck people's keywords. And they worked well for low-hanging fruit because they could generalize within the training space, but they didn't generalize outside the training space, so they never got there to language and inference. I expect the same will happen with deep learning. The failures of classification networks to extrapolate are a special case of what I've started calling the long tail problem, which you guys are probably pretty familiar with. This notion is that if you collect corpus data on pretty much any problem, you're going to get a distribution sort of like this, where there's a lot of corpus data for some common examples and relatively little data for your less common examples. The common examples are easy for many, many machine learning algorithms, and the rare examples are typically pretty hard. So, for example, you can download an app for your iPhone for the LabelMe database, and you can contribute to the machine learning of vision and possibly to the unemployment of you all as the machines get better at visual identification. But if you want to serve that cause, you're welcome to do so. And what people do is they take a snapshot of something, let's say a book, whatever is lying around, and you draw a little outline of it and you upload it to the database, and that's great. The database grows and grows and grows. And then someone more clever can go along and say, well, what are the properties of that database? And of course what happens is most of the people take pictures of books because they have books sitting next to them. Most people don't take pictures of aardvarks because they don't have any aardvarks around. And that means that the systems are good at recognizing books and cats and so forth, but they're not so good at recognizing other things. Watson isn't immune to this. Watson does a lot of machine learning, although not of the particular kind that I criticize, or not so much of it. But Watson, they decided from the start, basically what they were going to do, I have a quote from the technical paper, is they were going to use what was available on the web. And what's available on the web has a long tail issue. And that was fine. This is the secret I promised to reveal about why Watson works. 94.7% of the Jeopardy questions, which are the answers in Jeopardy, are titles of Wikipedia pages. So Watson works as well as it does because it's a very good information retrieval system. But Watson is not pushed towards genuine intelligence, if I can say that, because it doesn't have to deal with things that aren't titles of Wikipedia pages. So it doesn't have to confront the long tail problem. Watson is sitting in the sweet spot of the long tail distribution, which is the fat left-hand part, and that's why it was able to work as well as it did. It doesn't work 100%. There's also some issues about how fast to press the buzzer that humans will complain about, but even putting all that aside, the real issue with Watson is it can't do the kinds of things that people have been trying to do here at Vulcan. It can't, for example, understand a textbook because it doesn't have inferential abilities. So what's sort of literally written on the page, it can retrieve, but when it needs to go beyond it, Watson would be generally hard-pressed. I had different examples here, which is it would be lousy if you're trying to follow the plot of a novel, unless it's maybe a well-known novel. They actually deliberately excluded Project Gutenberg, so even if it is, they probably wouldn't do so well there. If you see like some story that is not out there in the literature, any one of you can go into a movie, start to learn who the characters are, what the relations between those characters are. Watson can't do that, wouldn't be able to handle a legal case involving little-known individuals. Intelligent creatures often deal with novel cases that they haven't encountered before, and not every answer is spelled out on the web. I think 85% of what's going on in AI today is vulnerable to this issue. When the answer isn't found on the internet, current machine learning techniques tend to fail. I wrote one of my New Yorker pieces about this work by Hector Levesque, my colleague Ernie Davis, and Leora Morgenstern, what they call Winograd schemas in honor of Terry Winograd. Those of you too young to know him should look him up. He was an advisor to Larry Page and Sergey Brin and did some pretty important early AI work. So there are examples like this. Joan made sure to thank Susan for all the help she had given. Who had given the help? If you're a human being, you can answer a question like this. You can figure out, based on your knowledge about words like help and what they might mean, you can figure out who was doing the help. Another example is the large ball crashed right through the table because it was made of styrofoam. What was made of styrofoam? The large ball or the table? People can do these things, but if they're not Googleable, if you're giving an example that isn't out there on the web, most machines are at a loss. What I'm doing in the last part of the talk, having been pretty negative in the first part, is to give some hints about how I think we might do better based on things that I've noticed basically as a cognitive scientist for the last 20 years. The first thing I'm going to do is, hint zero is not everything humans should do should be copied. So I don't want to just say anything that people do is something that should give a hint to AI, because some of the things that people do are probably not actually that great. Like our short-term memories, I alluded to this before, they're not even 7. We don't even have 7 plus or minus 2 buffers. We have about 4 plus or minus 2 buffers. Nobody would want to say, hey, we're going to, well, let me say this more carefully. I don't think it would be a good idea to go building AI systems that had short-term memory buffers that were limited to storing 4 pieces of information. I think that that would be tying our hands behind the back. No need to go there. Our long-term memory systems, I think they stink. You put information in, but you have no way of getting them out. Google obviously has a much better handle on how to have massive databases in which you can retrieve the information. I think we would be better off looking at systems where there are master maps and keyword indexes than trying to borrow from the human mind on long-term memory. Obviously, you don't want to borrow our mathematical precision, which is nil, and so forth. So our egos interfere with our capacity to reason. We often short-term considerations overrun long-term plans. I wrote about a lot of these things in my book, Kluge, and Kahneman wrote about them in his book, Fast and Slow. We don't want to just import willy-nilly anything that people do, because a lot of things we do are not so great. But I'll now give 8 or 9 suggestions for things that I think people do well that we would be advised to look at in trying to build AI. The first is I think we have a knack for inference. In the limit, you could argue that intelligence equals knowledge plus inference. And I'm alluding to the classic textbook, I think it's a textbook, by Nicholas Wirth, which is called Programs Equal Algorithms Plus Data Structures. I think you can argue intelligence is having the knowledge plus inferential techniques. The knowledge part of things is getting cheaper and cheaper. Big data basically is knowledge. It's become plentiful. You have things like DBpedia that encapsulate in machine-readable form things that would take human beings decades to learn or might never. But as I already said, even Watson is good on the knowledge side, but not on the inference side. Therefore, I suggest that going back to the human literature, and I think improving on it, might be pretty useful. Having a serious look from the perspective of AI at why is it that humans are better at making inferences, I think might be a profitable direction. The second is, and there is some overlap between these. I'll give you 9 ideas. I won't claim that they're 9 distinct ideas. They do relate to one another. Humans cope well with and have a high tolerance for inconsistency. So we all know that out of sight equals out of mind, and we also all know that absence makes the heart grow fonder. If you are in a classical logical system and you know those 2 things, you are done, right? In a classical logical system, from a contradiction you can derive anything. So once you allow these 2 into your system, you can infer that the moon is made of green cheese. And you don't want a logical system that concludes that because one contradiction happens to seep in. Human beings have ways of coping with contradiction. I think that there's been a bias, not 100% bias, but a bias in the AI literature towards looking for systems that achieve, or not even achieve, demand a higher level of consistency than humans seem to do. And I think that that's a profitable area for exploration. We also have a knack for knowing what inferential principles are relevant in a given domain. So we know, for example, if we're thinking about a human being as a physical entity or as a psychological entity. Usually we think about human beings as psychological entities, and when we want to manipulate other human beings, we think about what their psychology is, what would make them want to do this thing or that thing. Occasionally, this is an example from Steve Pinker, we think about them as physical objects, like there was a character in a TV show, LA Law. She was pushed down an elevator shaft. Her psychology at that moment ceased to be relevant. She was a character that nobody liked. And as she went down the elevator shaft, you started to think about her in terms of physical principles. So we have different micro-theories, to use a word that's been occasionally used in the AI literature. We're really good about knowing which ones are relevant in particular information. You can think of this as a kind of a gating problem of knowing which set of knowledge to use at particular times. I don't think there's ever been any really good cognitive science studies of how people do this. There are some really old studies that tell us that people can do this, but nobody has really systematically studied it. I think it would be really useful for AI if we had a better handle on that. Number 4 is generics. A generic is a sentence like dogs have 4 legs, which to use AI terms is defeasible. It doesn't have to be 100% true. And you can compare that to a universally quantified logical statement like for all x such that x is a dog, dog has 4 legs, x has 4 legs. Generics are not the same thing as first order predicate calculus quantifiers. Yeah, we're really good at them. Most machine logic systems tend to start with first order predicate calculus, and then people have debates about should I add in second order, third order, and so forth. But part and parcel of what humans do and what we teach our kids and so forth is generics, many of which are just statistical truths. And if it were just that, I think it would be no problem in AI, but it gets worse. So you say cars have radios, that's because most cars have radios. Maybe, it used to be in New York that a certain percentage of cars no longer had their radios. That seems to have stopped since the Giuliani era. But then there are some other kinds of generics that I think are not as easily captured in AI, and I think AI should look harder at these kinds of things. One example is ducks lay eggs. This is not actually a statistical truth in the sense that it's not true of the majority of ducks. There's a simple proof of that. I haven't actually gone out and tabulated ducks in egg laying, but I know that 50% of ducks are male, they don't lay eggs, and I know that some ducks are either not old enough or too old and so forth, and so they don't lay eggs. So my back of the envelope calculation is maybe 30% of ducks lay eggs. And yet we still think that there's a truth to it. Maybe I should put the words true in quotes as I did on the slide. But there's a way in which we understand this. We can make useful inferences from it, even though it's statistically a bit anomalous. And then there are even more puzzling cases, like mosquitoes carry malaria, which can be, quote, true, even if most mosquitoes don't. So when I tell you mosquitoes go to malaria, you should get a shot, can give you malaria, you should get a shot. You don't sit there worrying about, well, is it true that 98% of mosquitoes or 2% of mosquitoes? You get the shot and you understand what I meant. We're not so good, unless maybe people in this room are probably the people most likely in the world to have a solution to this. But in general, I don't think machines have really captured this. I know there's a lot of interest here in textbooks. Turns out even 4- and 5-year-old kids understand generics. I think if you look at textbooks, you will see a lot of them. More attention to how a 4- and 5-year-old can understand and reason about generics, I think would be a worthwhile avenue. Humans really care about causal principles. The easiest thing to get out of big data is correlation. So you can write a very simple music recommender system. It's very well correlated. People that like Dylan tend to like the Beatles. If they know one, you can suggest that they like the other. So there's obviously much money to be made from big data and correlation. Then we have Bayes nets that try to capture causal relations, but I think cause is represented in a Bayes net in a very thin way, which is kind of like there's a number on the likelihood of the cause or something like that, the probability of B given A. And I don't think this is how human beings think about cause. So again, thinking about kids or scientists, people are constantly searching for explanatory principles. We don't want to just know that X causes Y. We want to know why. Sometimes we settle for not very good explanations, but we're always looking for them, and I think it plays a role in our reasoning. So when a kid asks you, why is the sky blue, they're not asking you, what is the conditional probability that the sky will be blue, given this or that. They want to know what makes it so. They may settle for not fully understanding. But this is what I think people are trying to do. So the word of the day, thinking about Jeopardy and the Daily Double, the word of the day is apophenia, which is the kind of like pathological case of human beings' search for causal principles. Apophenia is the experience of seeing patterns or connections in random or meaningless data. For example, you have people that will look at sequences of lottery numbers trying to find the pattern, trying to find the causal principle. That's when the system, I think, goes too extreme. But we have the kind of brain that can go to that length that is looking for causal patterns. And I think in our better inferences, that's part of what's going on. We also have a knack for approximation and shortcuts. Generics are one example, but there are lots of others. For example, three-dimensional physical reasoning problems that you might solve by using a computer simulation that knew every molecule in perfect detail, we often solve, I think, by having a kind of one-dimensional or two-dimensional representation that's a cartoon or a caricature, a sketch of what's going on, rather than trying to model every detail. So if a cup of coffee spills, you see it start. If I start to spill this water, you can guess that Oren is at risk. He's not looking this way, and Peter is not, without having to calculate every molecule of my arm, what's in there, and so forth. So we often trade off reliability for speed. We have slightly less reliable answers that we get that are pretty fast, and we get good results. And I don't think there's any real cognitive science literature on how humans do this, but I think if there were, it might actually be informative with respect to AI systems. Related point is that humans are comfortable reasoning with incomplete information. So if I tell you I have a sealed box in which I have inserted a spider before I've sealed the box, and I shake the box and ask you, will the spider come out? And you can just tell me no. Whereas you can imagine a computer saying, well, can you specify the size of the spider? How big is the box? How many times did you shake it? At what velocity? What algorithm governs the spider's motor control system? And so forth, in order to give you a faithful simulation of what's going on. Ernie Davis and I are working a bit on this particular problem, trying to figure out essentially a logicist approach, although I think ultimately we need a hybrid approach, to try to understand how people reason about containers, which I think is a recurrent theme in a lot of things that we analyze, not just containers themselves, but for example, in biology, when you think about vesicles, vesicles are containers. Number 8, humans rely on many different learning algorithms and not just one. So there's always this quest for a single learning algorithm. But if you look at human beings, we do things like association and correlation detection, which are close to the things that are popular in machine learning. We also do things like observational learning that are not very well captured. I watch you do this, and then I try to do the same thing. I see you swing a baseball bat, and I try to do the same motion. We have explicit instruction. So I tell you, here's how you play Monopoly. This is what you're going to do. Right? Nobody learns Monopoly by digesting the recordings of 2,000 games of Monopoly and guessing what might happen next. We have specific systems that try to calibrate very particular information. Like I think that in our motor control system, we have ways of recalibrating relative to how much weight we're carrying at a particular moment. They're not perfect. The reason the teenagers are awkward is they haven't fully recalibrated their legs, which are growing quickly relative to the new weight and so forth. But I can give you a backpack, and you can compensate when you're climbing up a mountain. We have systems for automatizing or proceduralizing knowledge. So I tell it to you explicitly, this is how you should play these chords on a guitar, and then you practice it, and after a while you don't have to think about them anymore. We use inference to best explanation. We're trying to learn what's going on somewhere, and we don't know for a fact. We can't make a deductive inference, but we consider different plausible cases and try to guess what the best one is. Chomsky has a notion of parameter setting in linguistics, which is a kind of calibration for language where there are discrete possibilities for things like, do you have prepositions or postpositions? So does a word like with go before the noun that it's modifying or not? They seem to have very general properties across the language. The notion, I'm not sure I 100% believe it, or that it works quite the way that Chomsky suggested in the 80s, but the notion is we might have mechanisms that are looking for specific discrete pieces of information that calibrate systems. We look for taxonomies. There are lots and lots of things that we do. most of the learning systems, again, this room might be an exception, that I have seen are looking for this one silver bullet and not recognizing, analogy is a very important one that I left out, not recognizing that when humans solve problems, they have a lot of different tools to go after their problem. It's like people are trying to build the best power screwdriver out there, and that's great. I appreciate the progress. Screwdrivers are faster. There's enough torque now that you can use them as drills, but they're still lousy hammers. Number 9, common sense remains indispensable, even in the era of big data. And this one, I'm particularly sorry, is small. It's from a very recent vision paper. And they were trying to figure out why these vision systems tend to false alarm a lot, which is a problem I didn't realize, but makes sense. I just discovered this. They false alarm a lot. So you tune up your cat detector, and then you start seeing cats in places where there aren't cats. In this particular case, in the inset in the bottom right, well, the system has false alarmed to a car. There's a picture of a pond. The system says there's a car in there because it's an independent classifier. It's out there to look at cars. Vondrich et al. With Teralba at MIT did this particular work. The details of their work don't really matter here, but basically they figured out why the system thought that there's a car there, which is if you visualize what the feature detectors are actually doing there, and you look at the pixel level resolution, there's actually something that looks like a car there. But no human would look at this image and say there's this tiny little car that's murky that's just under the surface of the water. I could, with top-down knowledge, get you to believe that. I could have a movie that we describe and it's maybe a little toy car, and I could give a scenario. But unless I build up the scenario, you are not going to infer from this image that there's a car there, because you're using top-down knowledge and not just independent classifiers. And so in this way, I would call that common sense about where cars might be with respect to the surface of the water and what size they might be, and so forth. Common sense remains indispensable, even in the era of big data. Of course, I could have made this point in 3,000 different ways. I thought it was fun to make it with vision, because we don't always think about common sense with respect to vision, even though presumably we think about it a lot with respect to a biology textbook. And then I love this quote that I extracted from this paper, which is creating a better learning algorithm or building bigger data sets is unlikely to correct these particular errors. So there are some errors where the problem is you haven't seen enough training examples to know what a car is like. But here the problem is it looks like a car, but there's other reasons to think that it's not a car. So having a bigger database of cars is not going to help you. And nor is changing the 4th decimal place in your learning algorithm going to help you. That's just not the issue. The issue is you need some other kinds of knowledge. I think my numbering system leaves something to be desired. This is what happens when you work on your talk at the last minute. Number 10, or 9 prime, not counting number 0, is that brains are not blank slates. And I've already alluded to this, but I'll give one formulation of this. Again, I'm picking a different formulation than the one everybody knows. The one everybody knows for this point is Chomsky's argument that if you're exposed to a finite number of sentences and you extract an infinite grammar, essentially, Chomsky's arguing there's got to be something that's innate that allows you to do this reliably, or else you'd have a serious inductive issue. Spelke makes the same point with respect to our perception of objects. She says, if children are endowed innately with abilities to perceive objects, persons, sets, and places, then they may use their perceptual experience to learn about the properties and behaviors of such entities. It is far from clear how children could learn anything about the entities in the domain, however, if they could not single out those entities in their surroundings. I think this is a paradigm example of the kind of thing that we really ought to have innate knowledge of. There are lots of things out there in the literature, particular parts of Chomsky's linguistic theory that have been posited to be innate that I'm a little bit skeptical of. But the kinds of things that I think you really ought to have in an innate system are, first of all, the things that Kant talked about in the Critique of Pure Reason, which is my favorite early example of nativism. He basically says that you've got to innately have representations of time and place, and space, time and space. Spelke is saying, and you've got to have innate representations that there are objects, that there are sets, that there are persons. I guess place overlaps with Kant. I think those kinds of things have to be innate. And if you look at the developmental robotics literature, there's this weird sociology where people think, I've got to start from scratch. I don't know why they think this. I'm not sure. I mean, evolution didn't start from scratch when it built you. It built you on top of a primate. I don't know why the developmental roboticists are assuming that they can recapitulate 1 billion years of evolution in a couple graduate student career. I would say building in these kinds of things would be a much better start than just doing it by basically you have a retina, you have a learning algorithm, and you have a motor system, and you go from there. Okay. I'll give a very brief case study and then a remark that will slightly annoy 1 or 2 people in the room, and then I will wrap up. So here's the brief case study. how do you learn the meaning of a verb like eat? I'm not going to ask how you learn a noun because at least some cases are pretty simple. Concrete nouns, I can tell my son, this is a glass, and if I tell him enough times, he'll probably get it. And in a couple months from now, he'll certainly get it. Okay, but verbs are particularly hard because it's hard to point to them. So how do you learn a verb like eat? Well, the classic theory that any undergraduate will give you, or at least any smart undergraduate will give you if you ask this question, is really a version of a big data solution. What they'll tell you, and the technical name for this is cross-situational learning. So what you do is you hear eat in a lot of different sentences, and you try to figure out what's common across those sentences. And it's a reasonable theory, but it has some problems. One problem with it is that there are actually lots of examples where you hear eating and there's no eating going on. Lila Gleitman's favorite example of this is when the parent says, if you want to have your dessert, eat your peas first, or or just more simply, eat your peas, when there's not in fact any pea eating going on. So it's not clear that the big data solution would work. Maybe it could be made to work if you just did straight intersection across all the cases in which you had seen eat. You had heard the word eat. You would not, I think, come up with the right answer. But besides that, for humans, it's empirically wrong. So kids actually manage to acquire words just fine with relatively impoverished memories. Kids are not big data machines. My 12-month-old's memory is limited, but he's starting to make progress. He's learned about 60 words, which puts him ahead of, I think, the developmental robotics. Barely. But I'm optimistic, as I said. But he's not doing this by remembering every circumstance in which we say something. There's no way that seems plausible. Gleitman's recent work has been on what she calls propose but verify, which I think is a cute allusion to the Cold War, in which she suggests that word learning is essentially hypothesis testing. What kids are doing, and adults in laboratory experiments, is rather than steadily accumulating data, they're basically trying something on every trial. Could it be this? So you give a novel word, imperative, you give a novel word in some set of objects or events or whatever. She's done this with nouns as well as verbs. And what you find is that people are basically at chance at every trial. If you had a kind of system that was accumulating big data, you might expect that you're gradually getting closer and closer to the right solution, refining it a little bit. But what actually happens is people are at chance, they're at chance, they're at chance, and then boom, they've got it. There's a classic concept learning literature like this in the 1950s, the early cognitive psychological literature. So the way that I take this is humans can actually, to use a phrase from that I hear a lot at Google, humans can leave a lot of data on the floor. They don't need to take every piece of data and integrate it all in order to come up with the right answer. The reason that they can do that, Google can do that because they have so much data. This is why they use the phrase, they're kind of showing off. We can leave data on the floor. We have, 6 exabytes, and so, it doesn't matter if a couple of our servers fail. The reason, and that's true for them. The reason that humans can leave data on the floor, they do leave data on the floor because their memories are so bad. The reason that they can survive doing that is because their hypotheses about what things might mean are embedded, I believe, in top-down causal theories about the world. So they're not trying to sort of work it all out from bottom-up stuff. They have an idea what words could mean, and they're making guesses based on their notion about how humans think, about what words could be, and so forth. So the upshot of this is that kids use a small number of high-quality guesses rather than an exhaustive search or integrating all the possible experiences, which should remind you, if you know this classic literature, of chess. So machines play chess in a very different way from people, as you probably all know. Machines play by brute force. People, the grandmasters anyway, maybe not me, look at the board and they know like the 5 things that they ought to consider. I think kids are master word learners once they're about 2 years old. Okay, if deep learning is kind of the bull in the china shop, this is the thing that not everyone will agree with. If deep learning is the bull in the china shop that has been let loose on all of AI, sometimes with better results than others, then the elephant in the room that I have not mentioned is psych, and I feel remiss without mentioning it. This is Doug Lennett's Psych, which you should all know about but may not, which has a huge amount of innate knowledge that could potentially be integrated with bottom-up systems. It's geared towards common sense reasoning. It has some limited ability, I don't know how much, to deal with internal inconsistency through the use of microtheories, but relatively little is actually known about how effective it is. It's about 30 years old. I'm guessing that if we try to do the same thing now, we would do a much better job. We have much better quantitative techniques, for example. Lots of things that we know now that we didn't know then. But I think there'd be a lot to learn from psych's successes and failures. Because I think in some ways, psych comes closer to trying to do the kinds of things that I'm urging, certainly than deep learning does. So I think it would be a valuable thing to do to have a neutral external review of psych to figure out what it does well and what it does not. Okay, let me wrap up with a quote from Marvin Minsky from just a few days ago. He's, of course, 86 years old. He feels free to speak his mind, as he always did. And somebody asked him, well, when are we going to get real AI? He won some award. This is at the award ceremony. He says, it depends how many people we have working on the right problems, which I think is the exactly right answer to give. He said, right now there's a shortage of both researchers and funding. Artificial intelligence contributed many ideas and methods between the 1960s and 1980s, and then its influence became smaller. I haven't seen many advances in recent years because the money is going more to short-term applications than basic research. And the rest of this is my last slide, is basically a dissection of what he said. So Minsky has perhaps underestimated how much influence AIs have had of late. I mean, I think he gives a pretty pessimistic view. I think a lot of people would give more optimistic views. They might be impressed, for example, with Watson, with Siri, even if there are limits to them. I think he's also really seriously undervalued the many recent advances in machine learning. It's just not fair to say that nothing has happened since 1982 or whenever he stopped going to the lab regularly. Don't quote me on that. I shouldn't have said that out loud. But he is right that most of the money is going to short-term applications rather than basic research. And I really like this idea of research. A research program in AI might start by carefully investigating the few things that humans still do better than machines. And I thank you very much. I give a last word to Dr. Gary Larson, who has a cartoon that I think captures where a lot of AI is, even though it's about amoeba, in which the one amoeba says to the other, stimulus response, don't you ever think? Hopefully AI will start thinking someday soon.